So today we will talk about convex relaxations for non-convex nonlinear problems. So how is this related to the previous lecture, right? Remember in solving mixed integer linear programming problem, we need to do things called branch and cut, right? So we need to branch on the binary variables, and then we need to come up with tight linear programming relaxations for mixed integer linear programming problem, right? So essentially, for solving non-convex nonlinear programming problem, we need a similar method since we are interested in solving them to global optimality. So the method to solve general non-convex nonlinear problems is called branch and reduce. In this algorithm, there are also two major building blocks. One is branching, right? You need to branch on the, in this case, the continuous variables. Then the other major building block is convex relaxations, right? So in mixed integer linear programming, we need linear relaxations. And in non-convex problem, we need more general relaxation. We call them convex relaxations. Okay. So this is an overview of this particular lecture. We will first give you a quick overview of global optimization algorithm, i.e. branch and reduce. Then we will talk about some very commonly used convex relaxations. The other approach is using a linear approximation rather than relaxation. Also, we will talk very briefly about outer approximation for convex problems. Okay, so you probably have no clue what I'm talking about now. So let's go to the details, right? So what is convex relaxation? From this figure, you can get a very intuitive view of what is a convex relaxation, right? So here, let's suppose you are solving an optimization problem minimizing f of x, right? So in this case, f of x is clearly a non-convex function. The challenge of non-convex problem is that you can have multiple local minimum, right? A local minimum may not be a global minimum. In order to solve this type of problem, global optimality, the approach we will adopt is coming up with a function g of x, right? Denoted by this dashed line here. So g of x is a convex function, right? It underestimates the original function f of x. So g of x is called a convex relaxation or convex underestimator of f of x, right? So one property you can quickly see is that if you minimize g of x and get the minimum of g of x, right, it is always a lower bound on the original problem. Right? It's the same thing as linear programming relaxation gives you a lower bound of mixed integer linear program. If you come up with a convex under approximation of a non-convex function, this under approximation also give you a lower bound, right? Okay. Now with the lower bound, it is not enough, right? So if you solve this problem with a lower bound, you reach this point, you still cannot guarantee this lower bound is a global minimum for the original problem, right? Now, in order to solve a non-convex problem to global optimality, we need to do some sort of branching. Okay? So in this case, instead of branching on the binary variables, you may have to branch on the continuous variables as well. Okay? So here, let's suppose we branch on the continuous variables x here. Now you will split the relaxation into two parts. So you can split the original node into two nodes. And for each of the node, you come up with typically a tighter relaxation. So I will tell you what will be an example of dividing into subproblem and coming up with tighter relaxation. But geometrically, you can, for now, you can believe me that once you partition the problem into two subproblems, like here, the relaxation you come up with will be tighter than not partitioning. Okay, so as you can imagine, you keep dividing this continuous region into smaller and smaller regions, right? At the end of the day, the idea is the convex relaxation will approach the original function that is non-convex here, right? So as you can imagine, as you partition the domain of this problem such that each of the interval approaches a diameter of 0, right? Then the convex underestimator will converge to the original problem, right? So that's actually the intuition why global optimization methods converge. Yes?
If you have any discontinuities in your f of x, will this also handle that, or does this break down if there's discontinuities?
Yeah, very, very interesting question, right? If you have discontinuity, then typically what you will do is to model the discontinuity using some binary variable, right? You can, just like we model piecewise linear function, right? If your binary variable is 1, you are in this piece or in that piece. You can model this essentially as a disjunctive program, right? It's a disjunction over all the discontinuous pieces, and each piece you represent them using a continuous function.
And so then on each piece you would do this exact same thing, and
yeah.
then you compare across all the pieces.
Right. You can do that, right? That's sort of branching on the disjunction. This is like branching on the continuous domain. Okay. Yeah. Again, so the intuition is spatial branch and bound will converge in the limit. Right? You can imagine each of these interval becomes very small, and then the convex relaxation will approach the original function. Now, having said that, we do not want to solve a problem with infinite number of nodes, right? As the parameter goes to 0. So the challenge in global optimization is how do you derive tighter convex relaxation, right? So if your original relaxation is very close to this function, then you do not need to divide the problem into so many nodes, right? If the relaxation is weak, then you will end up with a large number of nodes. Okay? So that's a sort of key research question in global optimization. So the same analogy can be made in mixed integer linear programming, right? If you have some very strong cutting planes, then you get a good convex relaxation, then you don't need to do so many branch and bound iterations, right? The same thing here. But typically there is no free lunch, right? The strong relaxations can be expensive to solve. But in some cases you get relaxations that are strong, but also not so expensive to solve. That is the perfect scenario we are aiming for. Okay. So in order to study convex relaxations, let's define some basic concept. Right? So when we say tight convex relaxation, it will be interesting to say what does it mean by tight. Right? So, or in other words, what would be the so-called best convex relaxation you can come up with for a given function. Okay. So here, as you can see, I'm showing you f of x is a non-convex function, right? Denoted in this black curve here. Now you can come up with different convex relaxations for this black curve, right? For example, you could come up with a relaxation like this, right? Or like this, right? So what's special about this curve, this red curve here in the picture, compared with different convex relaxations, right? Just by inspection, without going to the math, how do you actually describe this? This red curve is kind of the sort of the best convex relaxation you can come up with, right? You cannot come up with any convex function that is greater than this red curve here, right? If you just move a little bit above this red curve, you are going to either end up with a non-convex function or you end up cutting off some of the black curve, right? So how do you describe this phenomenon mathematically, right? So the way to describe that is through something called convex envelope. Okay, so now the definition is given a convex function f of x, G of x is called the convex envelope of f of x if the following hold. First of all, we say G underbar x is a convex underestimator of fx, right? So it is always smaller than or equal to f of x. Then G underbar x is greater than equal to H underbar x for all convex underestimators, right? So essentially, G underbar of x is the convex underestimator that is greater than or equal to any convex estimator you can find. Or in other words, it is the tightest convex underestimator. Okay. So here's an equivalent statement, right? So what does it mean by it is tighter than any other convex estimator, right? How do you actually describe that? So here's an equivalent statement. It states the epigraph of G of x is a convex hull of the epigraph of f of x, right? So we talk about epigraph in the first few lectures of this course, right? So essentially, if you have a function f of x, right? So the epigraph is the area above this curve, okay? So the epigraph is this region here above the curve, right? Okay. Now what it says is, if you take the convex hull of the epigraph, right? So what is the convex hull of this epigraph? It is roughly, remember the convex hull of a set is essentially the smallest convex set you can find such that this set is contained in that convex set, right? So there are some equivalents related to convex underestimator and convex hull of the epigraph, right? So the convex hull of the epigraph is the smallest convex set you can find, right, that contain the epigraph, right? And the same thing in the function space is the convex function that is greater than or equal to any other convex estimator you can find, right? So that is called the convex envelope. Okay. And for the same argument, you can describe something called a concave envelope, right? So here, for this non-convex function here, the dashed line here is a convex envelope, right? And then this dotted line is the concave envelope, right? So how to describe the concave envelope? It is a concave function, right? The sort of the smallest concave function you can find to overestimate a non-convex function, right? So the convex estimator is the largest convex underestimator, right? And the concave envelope is the largest overestimator, right? Smallest overestimator. Yeah, you're right. Yeah. Okay. So how to describe that using in terms of sets? You can describe them using what is so-called the hypograph of the set, right? So the hypograph is the counterpart of epigraph, right? So it just describes the region that are smaller than the function value, right? That's called a so-called the hypograph. Okay. Yeah. So any questions related to the definition? Okay. So then let's talk about the convex envelope of the simplest nonlinear function, one of the simplest nonlinear function you can find, which is x times y, right? So let's assume we have a set described by this bilinear function, right? W equals to x times y, and then let's assume we have some upper and lower bound on x and y, right? And the goal is we want to find the convex hull of this set, right? Because after you find this convex hull, essentially you find both the convex envelope and the concave envelope, right? So you can think about this as this is essentially W less than equal to x times y W greater than or equal to xy, right? So you want to find the convex hull for the intersection of the epigraph and the hippograph, right? And then you get we essentially want to get the convex hull of this set. Okay. Right. So essentially, it is equivalent to finding the convex and concave envelope of W as a function of x times y. Right? Well, geometrically, you can take a look at this shape. Right? It is clearly a non-convex function. Right? If you plot that on a 2D dimensional space, and then with the function value, it is a 3D function. So this is like a saddle type of shape, right? We are, especially if you consider this curve, it is a convex function, and then you consider this curve, it is a concave function. Right? And that's an interesting thing about this shape here. Okay. Now, how does the convex and concave envelope look like for W equals to x and time y, right? It is very easy to see. You can plot it, right? The convex envelope are two hyperplanes, right? It's this hyperplane here, and then the other hyperplane is here, right? So it's the concave envelope are two linear functions, and similarly, the concave envelope are also two linear functions, right? Okay. And you can plot that to see why this is the case. Right? So the observation here is that the convex and concave envelopes for bilinear functions are linear, right? Just from this geometric intuition. So how do we derive the lower and upper envelope for bilinear functions? There is a very simple derivation. You don't need very sophisticated math, right? You only need probably middle school math to derive that. Okay. So let's set, remember x and y are also bounded, right? XL and YL are lower bounds for x and y. XU and YU are upper bounds for x and y, right? So therefore, if you set A equals to x minus XL, B equals to y minus YL, A times B should be greater than or equal to 0, right? Just because XL and YL are lower bounds, right? So if you multiply A times B, what do we get is the bilinear term x and y plus some linear terms of x and y and a constant term, right? So this actually gives you some linear underestimator of x times y. Okay, so this essentially gives you one of the convex envelope, right? So x and y is essentially the letter W we define here, right? Now, if you set it as xu minus x, yu minus y, right? A and B are both greater than or equal to 0. With that, you get another underestimator for x times y. So as you can imagine, you could also set, let's say, A equals to xu minus x, y equals to y minus yl. Then we have A times B greater than or equal to 0. So with this trick, you get a overestimator, and with the other combination, you got an overestimator, right? So with this very simple trick, you get 4 upper and lower estimator of the bilinear function. So this actually gave you the convex hull of the problem. Okay, very simple derivation. So this is called the McCormick envelope because it is derived by McCormick. Okay, so and then McCormick shows that this thing is the convex hull of the bilinear term, right? When x and y are both bounded. Okay, any questions so far? Right. So with this McCormick trick, can we apply the McCormick envelope to any quadratic constraint, quadratic program, and derive a convex relaxation for any quadratically constrained program, right? Because McCormick envelope gives you an upper and lower estimator for any bilinear functions, right? So quadratically constrained quadratic program is essentially composed of quadratic functions, right? So, or there are a bunch of bilinear terms when you have off-diagonal terms in the Q matrix. Just to refresh your memory, this formulation is called a quadratically constrained quadratic programs, right? When we are Q are the quadratic matrices, or you can think about it as a Hessian of these quadratic problems, right? And in total, you can have, let's say, K quadratic inequalities where X and Y are bounded, okay? So how do you derive a convex relaxation of a QCQP? Because a QCQP may be non-convex, right? So you want to derive a convex relaxation for the QCQP. One way to look at this problem is to formulate the problem in a lifted space. Okay. What do I mean by that is you can think about X transpose QX is essentially the inner product of Q times XX transpose. Right? Hopefully this is clear to you, because if you do matrix multiplication, this is essentially you have a summation over xi times xj times qij, and you sum over all of them, right? So it's essentially the inner product of Q and X transpose. Okay, so now let's define the capital X. Capital X is a n by n matrix to be XX transpose. And then you can linearize all the quadratic functions here, right? Because you did replace the variables. And then all the quadratic terms are replaced, and then you got some linear terms, right? Then all the nonlinearities will be gathered into this constraint, right? X equals to XX transpose. Okay. So what are the equations in X equals to transpose? It is essentially Xij equals to Xi times Xj. Right? Now, since you can apply McCormick envelope to any bilinear functions, you can apply McCormick envelope to each of these linear equations, right? And then get replace this nonlinear non-convex constraint with some linear relaxation. Okay, and then with that you can come up with a linear relaxation of a non-convex quadratic problem. Yes.
When we do this relaxation, how does that impact our computational efficiency? Because isn't this doesn't it take twice as many computations now in order to build this envelope as if we were just following the function itself?
Right, so you end up with a large number of constraints, right? Than the original number of constraints. That is, you will end up with a linear problem, right? After you derive the McCormick envelope. The original problem is non-convex, non-linear. You may end up at a local minimum point, right? So that's why you want to derive convex relaxations. But the nice thing is that they are linear, right? Yeah. Okay. So this trick is a basic in solving quadratic problems. Right? If you write a non-convex quadratic problem and fit it into Groovy, and Groovy will automatically come out with these convex relaxations. Okay, and then the commonly used convex relaxations are these type of linear relaxation derived from McCormick. Yeah.
Wait, so whenever you say that, does that mean that if I give it to Groovy
Yeah.
in this form, it will figure it out? It won't. But if I put in the full problem without having done the relaxation, it won't figure it out?
Oh, so you feed into Groovy this QCQP form,
Yeah,
right?
yeah.
So
Like
you
if
write the
we-
problem in this form, like let's say the pooling problem or facility location problem. It is in this form, right? And then how does the algorithm in Groovy work? It will automatically convert this problem into this form with the McCormick relaxation.
Okay,
So it's,
gotcha.
at the root node, it solves the linear programming relaxation.
Okay.
Okay, yeah. other questions here? Yeah.
The lifted QCQB is something similar to relaxed by SDP.
Oh yeah, so in SDP you also formulate the problem in a lifted space. Yeah, that's true, right? So but here, this lifted QCQP is equivalent to the original problem because you just did a replacement of variables, right? But since this constraint is non-convex, you can relax it by some linear constraints, right? The SDP, I will go to SDP later. It relaxes this constraint in a different way. Okay. Yeah.
What is the meaning of that lifted space?
The lifted space, well, the meaning is you would like to do some replacement of variables, right? Instead of having the product of variables, you define some additional variable that represent the products of variables. Then you replace this equality constraint by some convex relaxations. Okay. Yeah. Now, so a tricky, yeah.
Can I ask also a question? So is it true that we can formulate polynomials of any power SQCQP then and solve it this way?
And
I mean, if you have x cubed, we have x cubed equals, I don't know, t, and then t by x.
Yeah, that's a very good point. I will cover that later, right? So if you have polynomial function, we can convert it, just like you said, you can decompose them into quadratic problems. Yeah, that's a very good point. Okay. Now, a tricky question here is when you first study global optimization, it is easy to get confused by the idea of convex envelopes, right? So we said McCormick envelope is McCormick envelope is a convex solve of the single bilinear problem, right? You can see that in the picture. But now, if you apply McCormick envelope to a QCQP, right, would you get the convex solve of the QCQP? Right. So by definition, the convex solve of the QCQP is defined by this set, right? You have to include all the constraints in the QCQP, right? So and the X and the capital X have to satisfy all these constraints. So if you apply McCormick envelope to the feasible region of the QCQP, do you get the convex solve of the QCQP? You said no. Can you explain why?
Because when we find our hole, it's possible that we could have gotten a tighter fit if we ignored the sides that are in.
Yeah, that's a very good intuition, right? So mathematically speaking, it is like you have two sets, right? So set A and set B. You get the convex hull of A and convex hull of B, then you intersect with the convex hull. So the idea is think about McCormick envelope as you convexify one bilinear term, and then you convexify another bilinear term, and you intersect with them, right? And then if you want to get the convex hull, you should get the convex hull of the intersection instead, right? So these two things are sometimes the same, sometimes different, right? So the right-hand side is you convexify two sets separately, and then you intersect them. That's like what we did when we apply McCormick envelope to each bilinear constraint separately, and then we'll put all the McCormick constraint together, right? It's like this right-hand side. And the left-hand side is saying you first intersect all the nonlinear constraints, and then you take the convex hull altogether, right? So you can show mathematically the left-hand side is a subset of the right-hand side. Okay, so why is that the case? You can show that mathematically yourself, right? But I want to give you some intuition why this is the case, right? So now let's consider two sets. These two sets are both non-convex, right? Now, if you consider the convex hull of the intersection, right? So if intersect set A with set B, that supposedly have like a zero intersection. Like they don't barely touch each other, right? Then the convex hull of the intersectional set A and B is an empty set. Right? Because A and B are both non-convex, let's assume there's some distance here, they do not touch each other. Right? So therefore the convex hull intersection of A and B is an empty set because the intersection is an empty set. Right? But if you consider the convex hull intersect with convex hull of B, right, it will look like something. So the convex hull is something like this, right? The convex hull of B is something looks like this, right? So clearly they have some non-empty intersection. Okay. Yeah. And also, you can show if A and B are both convex sets, then they are equal to each other. Right? Since we are convexifying non-convex set, then you do not have this property here. Okay. Now, after we introduce McCormick envelope, you can think about you could solve the problem we introduced in the previous lecture. At least you can come up with some convex relaxation for the problem we introduced in the previous lecture, right? Like the packing problem, continuous facility location, pooling problem, right? Another well-studied application is called AC optimal power flow problem in electrical engineering. Now, I still owe you something we talked about in the previous lecture, right? In the pooling problem, remember we covered 3 different formulations, the P formulation, Q formulation, and PQ formulation, right? I said PQ formulation is better or tighter than the P formulation or the PQ formulation, right? Although, the problems are, the non-convex problems are equivalent, but their convex relaxations are different, right? So the reason you want to formulate the pooling problem using the PQ formulation is because after you apply the McCormick envelopes, the PQ formulation is tighter than the P formulation and the Q formulation. That's why you prefer the PQ formulation. Okay. And for pooling problem, you can observe that if you use the PQ formulation, the McCormick relaxation is actually pretty good. Right? It's very simple to derive, but for some of the problems, McCormick relaxation is pretty good. Right? It gives you usually less than 5% optimality gap compared with the original non-convex problem. But for some other problem, like packing problem or continuous facility location or AC optimal power flow problem, the McCormick relaxation are usually pretty weak. Right? So then for that problem, either you need to do a lot of branch and bound, or you should come up with stronger relaxations. Okay, that's sort of some empirical view on the McCormick relaxation. Now, since you mentioned SDP relaxation, right? So let's revisit SDP relaxation again, right? So how do we derive the SDP relaxation? Remember, we have this non-convex constraint, right? The lifted variable equals to x times x transpose. In the McCormick relaxation, we replace these non-convex constraints with linear relaxation or McCormick envelopes, right? Now, there are different ways to come up with convex relaxation. You can also relax this using semi-definite programming, right? So the way you relax that is the following, right? You can relax this equality constraint by PSD constraint, right? So remember this constraint means the matrix X minus XX transpose. So this matrix is positive semi-definite. Right? Okay, so why this is a relaxation is because, in the original non-convex constraint, X minus X transpose is a zero matrix, right? In the non-convex formulation. This thing is essentially a zero matrix, right? Of course, a zero matrix is a positive semi-definite matrix, right? So they are relaxing the constraint to be a positive semi-definite, right? And by Scher's lemma, this constraint is equivalent to this bigger matrix being positive semi-definite, right? If you forgot about that, you can revisit Scher's lemma. These two constraints are equivalent, okay? So why do we need SDP relaxation, right? So if you try to solve a problem using the SDP relaxation, typically you will find SDP problems are very expensive to solve, although it's a convex problem, right? So empirically, not always NP-hard problems are more time-consuming than polynomial problems, right? So for example, mixed integer linear programming is NP-hard, right? But then semi-definite programs are polynomially solvable, right? But if you have a practical problem, what you care about is not this asymptotic convergence or asymptotic complexity, right? You don't care about when the size go to infinity, how will the computational time grow, right? You are dealing with finite size problem. So even maybe SDP, although it's a polynomial, the constant term can also kill you, right? So in practice, usually SDP is very difficult to solve, okay? But the nice thing about SDP is it works pretty well for some of the non-convex problem, like AC optimal power flow problem. The McCormick relaxation is very weak, but SDP relaxation gives you usually very good relaxation. Okay, but in general, SDP relaxation is incomparable to McCormick relaxation. You cannot say one is always tighter than the other, right? So in practice, if you want tighter relaxation, you can add both, right? You can add both the McCormick inequalities and the SDP constraint. And of course, there is no free lunch, right? If you add more inequalities, the relaxation is more difficult to solve. Okay, so I said SDP relaxation is difficult to solve, right? You could solve that using interior point solvers like Mosaic, right? But it can be quite slow. On the other hand, linear programming solvers are usually much faster and more robust. Yes?
So you said that we can just add the inequalities for each of them, for SDP and for McCormick.
Yeah.
But then we obviously have more inequalities there. But when we plug it into like Garobi, doesn't it do a pre-solve and it would eliminate any of the superfluous ones? Would it only keep would it keep some from each to keep the tightest inequality, or does it not do that?
Yeah, that's a very good point. So you do not need to add the convex relaxation. You do not need to add those inequalities by yourself, right? If you are just interested in solving a QCQP, Garobi does that automatically for you, right?
Does it?
Yeah, but it does something very similar to what you said, right? It will add those relaxations on the fly rather than saying add all the cuts at the beginning, right? So it has very good heuristics to add, especially SDP cuts. So which actually I will talk about next, right? Yeah, so typically in solvers like Garobi, they will not directly solve the SDP, right? So they will add some linear cuts derived from the SDP. Right? Remember we talked about an algorithm to solve SDP, right? It's a cutting plane method to solve SDP. After you solve the LP relaxation, and then you check the eigenvalues of this capital X matrix, right? If all the eigenvalues are positive or non-negative, then you already satisfy the PSD constraint, right? If some of the eigenvalues are negative, then you could take the eigenvector corresponding to that eigenvalue and add this cut V transpose XV, right? The V being the eigenvector corresponding to the negative eigenvalue. Right, so that's actually what the solvers will do. Instead of solving SDP directly, it will add some linear cuts related to the PSD cone, right? now, like Zach, what you said, how to find the good, so-called good cuts, right? It is still an active area of research, how to find good cuts, because you want to balance the quality of the relaxation and the speed to solve the relaxation, right? If you add too many cuts, it can slow down the solver as well. Okay. Now, typically, the heuristic is to make the bound improve, but you also want to keep this vector v sparse, because if the vector v is very dense, right, you will end up adding a linear constraint that has a lot of non-zeros, right? Remember when you take matrix inverse in solving linear programs, right? You want to leverage the sparsity of the matrix, right? If you add too many cuts that are very dense, it will slow down the linear algebra of the solver. Okay, so therefore you could select some of the so-called sparse cuts. Typically, people find let's quote some good principal minors of the PSD matrix instead of adding a dense cut. Okay, any questions for this part? Okay, so now we will talk about another philosophy of deriving convex relaxations. This thing is called difference of convex relaxation. Okay. The idea is the following: if you have a function f of x, right? F of x may not be a convex function, but you may be able to represent a non-convex function as the difference of two convex functions. Okay. Why that is the case, right? So let's maybe give a quick example, right? So let's say you have So let's say you have f of x and y, right, equals to a bilinear function. Okay. Now, can you represent a bilinear function as the difference of two convex functions? Yeah. Any tricks we can do here?
X plus y squared minus x minus y squared.
Yeah, right. So you could represent this as x plus y square minus x minus y square. Maybe you should divide by 4, right? Okay. So these two functions are convex functions, right? Right. And then if you take the difference of them, you can get this non-convex function. Okay. So that is a high-level idea. Okay. Now, of course, if you do this simple replacement, it's like doing nothing, right? You just represent the original function in a different way. However, if you can replace this minus qx, right? So qx is a convex function, then minus qx is a concave function, right? So if you can have an underestimator of this concave function minus qx, then you come up with a relaxation of the original. Come up with an underestimator of the original function, right? Okay, again. So you want to the goal is you want to come up with some under-approximator of function f of x, right? Which is you want to come up with some underestimator that is convex. So you represent f of x as the difference of a convex function, or you can think about this as a convex function p of x plus a concave function minus q of x, right? So the first part is already convex, right? You are good, right? But the second part is not convex, it's concave, right? If you can come up with a convex underestimator of the concave function, then that will you will get a convex underestimator for the whole function f. Right? So how do you come up with an underestimator of a concave function? We will talk about that later. You can think about, let's say, so this is a concave function, right? Supposedly I'm only interested in some regions XL and XU, right? So this is a concave function. I'm interested in regions between XL and XU. How do I come up with a convex underestimator of this concave function?
Just a line.
Yeah, it's just a line, right? Okay, actually the line is the tightest convex underestimator of this concave function, right? So with that intuition, this difference of convex relaxation give you a recipe of constructing convex relaxation, right? Because a concave function is easy to relax, you can just use a line to under-approximate that, right? Okay, so now with that, how do we generalize this idea to any non-convex function f of x, right? So one possible decomposition of the DC decomposition of any function f is you add some square term, right? So you add mu plus summation over I xi squared, and then you minus the same summation, right? So the argument here is for sufficiently large mu, right? The first part, so the first part will be convex for large enough value of mu, right? And the second part is just some square term, right? It's very clear this part is a concave function, right? It's a minus of xi squared, right? Now, a quick question is why this claim is true. For sufficiently large mu, the first part is convex.
Because like once U gets big enough, when your like quadratic term dominate,
Mhm.
the whole thing, and since it's quadratic, it'll always
Mhm.
be convex.
Right, yeah, exactly right. So let's assume it's the functions are differentiable to the second order, right? So let's assume the Hessian of function f is a bounded Hessian, right? Let's assume it's not positive semi-definite, right? The Hessian of the term you add is nothing but mu times 2 times the identity matrix, right? So when mu is large enough, you are adding some large term to the diagonal of a matrix, right? So there is a sufficient condition for a matrix to be PSD, right? It's called diagonal dominant matrix, right? If your diagonal term is dominant all the other terms, then that matrix will be PSD, right? Okay, so now you can think about you have the difference of convex functions. The first term is this P of x, right? F plus mu times the square terms, and the second term is the quadratic term, right? And you can always relax Q of x by McCormick envelopes, right? Or you can think about by relaxing this by a line. Actually, the McCormick envelope will be this line, right? If you have a quadratic function here. Okay. So how do you calculate mu is a good question, right? You do not want to get the mu to be too large. If the mu is too large, then the relaxation will be weak, right? Although you know for large enough mu, this will be a valid relaxation. But otherwise, on the other hand, you don't want the mu to be too large. Okay. So let's talk about how do we get the mu's for QCQPs instead of for general nonlinear programming problem. If you're interested in general nonlinear program, you can check this paper by Chris Fludas on this so-called alpha BB algorithm. Chris Fludas is also a chemical engineer working on global optimization. So, and then the alpha BB is a general way to derive good mu's for for general nonlinear programming problem. But let's show some quick example on QCQPs. Right? Let's say you have a quadratic function, right? You are going to perturb them by mu times this part, right? Then what should be the value of mu you are going to choose? Okay, for this problem, you can choose mu to be the negative of the smallest eigenvalue, right? Because if you add the negative the smallest eigenvalue, right? If this part is not PSD, that means the smallest eigenvalue must be negative, right? And then you add minus the smallest eigenvalue, then you will get a PSD matrix. And then this is like a uniform perturbation. You choose mu to be uniform for all the quadratic terms. But you can also do a non-uniform perturbation of Q, where you add some alpha term, which is a diagonal matrices, right? For different xi squares, you are going to choose different values, right? So this part is essentially a sum over alpha I xi squared. Right? So this perturbation for different xi's are different in this case, right? Here you have a unique mu outside the summation. Okay. Now in this case, in order to choose a good alpha, essentially you want to satisfy this particular PSD constraint, right? Q plus the diagonal matrices alpha is PSD. And as long as this holds, it will give you a valid relaxation. Okay. Now, let's talk quickly about a convex envelope of a univariate concave function. We already talked about it before, right? If you have a univariate function and then x is between a and b, and then you want to get the convex underestimator of this function, essentially it's just a line connecting these 2 points, right? And that is the convex envelope. Now, quick question, what is the concave envelope of a concave function? Yeah, a function itself, right? Just make sure you are still awake. Okay, yeah, so that's, the concave function, concave envelope is function itself, right? You only need the convex envelope, right? So in other words, then the concave envelope of a convex function is also a line, right? And similarly, you can apply it to this normalizing concave function. Okay? Yeah, now it comes to the procedure for bounding any arbitrary nonlinear functions, right? So we talk about how do you bound bilinear functions, how do you bound concave functions, right? But in reality, you may have a function as nasty as this one, right? How do you come up with a convex concave envelope for this very nasty function? Unless you are super smart, it's very hard to do, right? So in practice, what people will do for these composite functions is sort of decompose them by univariate operations, and then derive convex envelope for each of these univariate operations, right? Just like you said, if you have a polynomial function, you can always decompose them into bilinear terms and apply McCormick, right? So let's see how we do that, okay? So the idea is to apply these type of relaxations recursively to the problem. Usually you apply it from within this expression, right? So let's first convert these simple functions by replacement variables. You can replace x times y with x1, okay? Then you have z times the logarithm of w. You don't need to, we haven't talked about how do we come up with a relaxation for z times log w, right? What we have covered is you can come up with a relaxation for log w itself, right? Because it is a concave function. So now let's replace log of w using x2, right? Now this term will become x2 times z, right? It is a bilinear function we do know how to derive convex relaxations for, right? And now let's replace z times x2 by x3. Okay. Now with that, we define x4 being the summation of x1 and x3. It's a linear function, right? So with this replacement, you have an exponential of x4. We do know how to get convex and concave envelope for exponential function because it's a convex function, right? Similarly, you can replace z raised to the power of 3 by x6, right? So if we still don't know how to come up with a relaxation for this function, you could further replace it by quadratic functions and come up with McCormick envelope, right? Then x7 is x6 times x5, right? So this is a bilinear function. You still know how to relax it. And f is the square root of x7, and then we know how to relax it, right? In other words, you are going to decompose this very nasty function into these univariate functions, which you do know how to relax them, right? So if you do this, let's say, lifted reformulation, it is exact, right? But then you can always relax each of these terms separately, and that will be a relaxation for the original problem, right? So this is replaced by McCormick. You can replace this by this secant or linear underestimate, and so forth, okay? Okay, so that's what the solvers like Barron or Gruby will do if you give it an expression like this, right? You will decompose it into easy expressions and come up with relaxation for each of them separately, okay? Yeah. Now, here's some examples of multilinear terms or polynomial functions, right? What is multilinear term? That means you have a polynomial where the power of each of the variables x is always 1, right? But then you can have multiple xi, right? Like x times y times z. It's a multilinear function. Polynomial function means this alpha I can be any positive integer number. That is called polynomial function. To decompose polynomial functions, for example, z equals to x1 squared times x2 times x3, right? You can decompose this problem to quadratic problems, right? If you set, say, y1 equals to x1 times x2, y2 equals to y1 times x1, and then z equals to y2 times x3, right? This is one of the ways of factoring z. For polynomial functions, it is very easy to see factorization is not unique, right? There are different ways of factoring this function. You can also factor them by let's say y1 equals to x1 squared, and then y2 equals to x1 squared times x2. Equals to y1 times x2, and then z equals to y2 times x3. Right? It is a different factorization. Now the practical implication is if you are interested in solving polynomial optimization problems, what the solver will do is it will find a so-called good way of factoring that into QCQPs and apply relaxations. There are also special relaxation built for polynomial optimization problem. We will not cover that. You can assume what the solver will do is converting the polynomial functions into factored quadratic functions, and then you apply the relaxation you already discovered for quadratic functions. Yeah.
Do we need to do something like this, or we go
No, right.
If we have polynomials, it does it.
Yeah. So now with the latest version, it should be able to automatically handle that. Right? If you came to my class a year ago, it couldn't. Oh yeah. So now it was able to do that. But for the mixed integer nonlinear programming solvers like Baron, Antigone, they were built for solving this type of problem. Right? Even like 10 years ago, they could already do that. Okay. So the other thing we talked about many lectures ago is so-called piecewise linear approximation of non-convex function. Right? If you have a super complicated non-convex function, it's very hard to relax them. Right? The fallback strategy is to convert them to mixed integer linear programming problem. Right? Remember we've talked about this when we talk about the SOS2 special order set 2. Right? So for any convex function, you can pick some point and do a sort of linear interpolation of this non-convex function. But of course, you will suffer from accuracy, right? It's not exactly the non-convex function, but for some of the practical problem, maybe you do not care about accuracy that much, right? A piecewise linear approximation is good enough. This is especially true if the non-convex function is in your objective. Right? You are trying to approximate some cost, then it should be fine, right? However, if the non-convex function describes some sort of physics, like power flow or flow in the pooling problem, right? At least you need to satisfy mass balance, right? Then if you do linear approximation, it probably would not satisfy. You need many linear pieces. Some people try to build solvers just based on piecewise linear approximation, and then try to add these breakpoints dynamically based on the solution. So in order to formulate that problem, just to recall, we could use a special order set 2, right? The idea is when you are in a given pieces, only the two adjacent breakpoints are activated, right? So if you are in this particular piece here, you only care about these two adjacent breakpoints, right? All the others are ignored. So therefore, if you write the problem as a disjunction, the binary variable should follow some SOS2 constraint, meaning that only the two adjacent binary variable can be equal to 1 right, at a given time. Okay, so here's what we had before. Right? X is a summation of over lambda I xi, and lambda i's are the summation of lambda I equals to 1, and lambda I follow the SOS2 constraint, right? Meaning that only two adjacent lambdas can be non-zero. Okay. Yeah. Now, another thing I will describe very briefly is what if we have a convex nonlinear function and we would like to come up with a linear relaxation, right? So if you want to take advantage of linear solvers, you do not want to, for example, if you do not want to use interior point solvers for convex nonlinear programs, right? Because they are not as robust as linear programming solvers. So in solvers like Groovy and Baron, usually they will generate so-called outer approximation cuts for convex nonlinear functions, right? instead of directly solving that convex nonlinear problem. The idea is the following. Here, this red curve is a convex nonlinear function. Right? So how do we approximate the convex nonlinear function? Right? One trivial way to approximate is using this first order characterization of convex function. If you linearize a point using first order Taylor series expansion at any point in the convex function, it always underestimates the convex function. Right? That's what we talk about for convex functions. Now, the challenge here is, where should you do the first order Taylor series approximation? Right? There are infinite number of points you can choose to under approximate the convex nonlinear function. Right? There are always trade-off. If you use too many points, then the LP will be slow. Right? You are adding a bunch of linear inequalities. But if you only choose one of the points, then it is a very poor approximation. Okay. And the idea is we want to be a bit parsimonious in choosing the linear under approximator, but then we want to add them at so-called good locations of this convex function. So in the solver by Professor Tawamalani and Professor Nick Sahnidis, right? So this was developed when Professor Mohit Tawamalani was a PhD student, and then they proposed different ways of choosing the outer approximation cuts. Okay, so I'm not going to the details of these rules. For example, here, if you have an interval, right, you could always choose the middle point of this interval and add this OA cut, right? And the other heuristic they said is instead of bisecting the interval itself, you will add a cut that bisect the slope of this function. Right? So on the two sides of the interval, you have this line with a given slope and this line with a given slope. Right? You can pick a linear approximation cut that bisects the slope of the two endpoints rather than bisect the interval. Okay, and there are other different ways, right? Like maximum projective error, right? Maybe you could, I don't know exactly mathematically what this means. Could be you want to sort of maximize the size of this ball here. Okay. Now, if you are implementing a global solver, right? One of the challenge here is how do you identify which function is convex, which function is non-convex, right? If you recognize a function is convex, then you could just do outer approximation. You don't need to factor that function anymore. Right? So convexity detection is still one active area of research. Right? There is no sort of general rules for giving you the necessary and sufficient condition for any arbitrary function being convex or not. However, you can use the rules we studied in lecture 2. Right? There are different rules saying, there are some basic functions, they are convex, but then there are also some operations that will preserve convexity. Right? This is slides I copied from the second lecture. Right? For example, if F1 all the way to Fm are convex, that implies their weighted sum with positive weighted sum are also convex. Right? There are other rules like affine combination or pointwise maximization that preserves convexity. Right? That's what the solver will do underneath the hood for you. If you throw an arbitrary nonlinear problem to the solver, how would the solver detect which function is convex? Right? They actually follow those not really heuristic rules, but they have a recipe of convexity detection. Right? But then how comprehensive is that recipe? It really depends on the solver. There is no golden rules that work for any problems. Okay, so that's almost all I want to cover in this lecture. Again, if you are interested in more theoretical details, you could refer to these two classic textbook on global optimization. Okay. Any questions? Yeah.
What is, it might sound like a little bit vague, but what is a big problem when it comes to quadratic problems? When it comes to linear, as far as I understand, like millions of variables, millions of constraints, it's okay, like we can solve in seconds. But when it comes to quadratic, just a non-convex quadratic, QP, so what's the...
Yeah. That is a great question. I should have covered that in this class. So let's just spend another 5 minutes, since we have 5 minutes here, talk about that, right? Yeah, again, this is just orders of magnitude, right? It could be problem dependent. So let's talk about, for different types of problem, what will be the state-of-the-art solvers able to solve nowadays, right? In other words, what would be a big problem in today's standard, right? So we could talk about not just QCQP, but maybe let's start with linear programs, and then we can go to MILP or QCQP, right? And then, yeah, so most of this in this class, we talk about global solvers, right? Okay, and then maybe we can have local solvers as well here. Then we could also have maybe general nonlinear programs, and then let's talk about mixed integer nonlinear program. What would be the order of magnitude of problem you could solve? So for LP, many people believe LP is very mature. I disagree with that, because the people who believe you cannot, you can always solve the LP is because they don't have a large enough problem, right? For really realistic size industrial problem, LPs, I wouldn't say LP is so easy to solve. Maybe the research could be focused on problem with, let's say, 1 billion variables also, right? You could do very simple calculation. When you talk about big problem, one is CPU time, the other is memory, right? So you could do very quick calculation to check how much memory will 1 billion variable consume, right? For some of the big LPs, for example, we have a server with 1 terabyte of memory. You cannot even load the LP into the memory, right? So let's say you could, for example, of course, for LP, you are talking about global, you could say around 1 billion variable. For MLP, the large problem you can talk about rather, let's say, 1 million variables. For QCQP, it could be quite problem dependent. If you are, I would say for all these problems, if it's non-convex and then quite nonlinear, you could just talk about 1K to, let's say, give an arbitrary orders of magnitude, maybe 100K type of variables, right? For very challenging non-convex MLP problem, even a few thousand variables can make the solver struggle, okay? But then for all these methods here, you could use a local solver, right? Especially for QCQP. Let's see. So local solvers, we could talk about, let's say, QCQP and NLP. You could always use the interior point solver to solve this problem, right? Because the interior point solver will return a KKT point for you, right? Although it may be a local minimum, but for some problems, a local minimum is already pretty nice, okay? So if you use interior point solvers, which is a local solver to solve QCQP or NLP, you can talk about problem of roughly 1 million variables. Okay, yeah, that's my overall impression. It could be outdated. We could update this number over the years. Okay, any questions here? Yeah.
Did you ever use like cascade methods where, let's say you have a coarse mesh of so to do a global, if you're trying to find like the perfect shape for like CFD or something, and then you use that to have the general shape, and then you would put that into a local to solve with like a finer mesh. Is that something that people do, Or
Oh.
if you can find the global, you already have.
You mean for like shape optimization
Yeah.
in CFD simulations?
Yes.
Okay, yeah, I'm not an expert in that because for that problem you are talking about optimization with PDE constraints, right? I'm not an expert. I don't know exactly what they did in the shape optimization.
Okay.
I would not believe they can solve those problems to global optimality, right? Especially how do you represent a continuous curve, right? I would assume they will discretize that in some way, just like you discretize the PDEs, right? But if you know more, you could tell us a bit more about that, then people can learn from you. Okay. Yeah. Any other questions? Okay, great. Thanks for asking that question.